Alright, so in the previous segment we had written this explanation. We said more mass causes there to be more inertia. More inertia is more resistance to changes in motion. That's the definition there of inertia. More resistance to changes in motion make it harder to oscillate. There's an elaboration. Harder to oscillate means it's going to take more time to oscillate. And of course, that is the definition of period. So it will mean more period or longer period. There is an explanation for why mass, the independent variable, affects period, the dependent variable. More mass means more inertia, which means a longer period. But then we also have these elaboration and definitional steps or links in our logical chain. Now, this whole shorthand thing can be put down into words, and that would be the expectation when you write an explanation. Let's show that. Okay, so our shorthand explanation, here again is our traits, and here's the shorthand translated into a paragraph. So, an increase in mass means a larger amount of inertia. Larger inertia means the object has more resistance to changes in motion. Larger resistance to changes in motion means it's harder for the inertia balance to oscillate. If it's harder for it to oscillate, it will take longer to oscillate. And if it takes longer to oscillate, it means it has a longer period. That's an explanation for why an increase in mass causes a longer period. Now let's do another explanation, this one a little bit more challenging. Alright, so here's a more challenging explanation. Why does increasing the mass of the pendulum have no effect on the period of the pendulum? Remember, the pendulum is a mass hanging at the end of the string that swings back and forth. Alright, well, let's go ahead and write our explanation. First, let's identify the key concepts that might come into play here. Assuming we're holding everything else constant, then we're not going to be changing the oscillation distance because that's only affected by the length of the string and how far we pull it back. You can see that there. Now, if we're changing the mass, then we are likely changing the inertia and the centering force of weight or gravity. Now, we want to make sure that the pendulum actually has gravity as a centering force. So hopefully that's something that you can see and understand, but our chart here shows that the pendulum, in fact, does have weight as a centering force. So by changing the mass, we're going to be changing these two things. Let's go ahead and write our explanation. Let's do one of those changes at a time. So, increase in mass should cause an increase in the amount of inertia. The increase in the amount of inertia is the same as an increase in the resistance to changes in motion. If there's an increase in the resistance to changes in motion, that means it will be harder to oscillate. And if it's harder to oscillate, that means it's going to take more time to oscillate, which means it'll have a longer period. But wait, we're supposed to show that it has no effect on the period. So that can't be all. And in fact, it's not. As we talked about earlier, the mass influences the weight, which is the centering force. So let's see what that chain of logic shows us. Greater mass means a greater period, a greater weight. All right. And a greater weight means a greater centering force. Greater centering force. That means as this pendulum swings up here, gravity is pulling on it to try to slow it down and then pull it back to the center. And as it swings back this way, gravity pulls on it to slow it down and then pulls it back to the center. We'll finish the rest of this explanation in the next segment.